for coming, everybody. It is my great pleasure today to introduce Daniela Doneva, who's going to give today's seminar. So Daniela did her PhD in Bulgaria at the University of Sofia, and then she moved on to Tuebingen as a postdoc, having several positions there, and currently also having a fellowship of the Learner program. And please, take on. Thank you very much for the introduction, Alex. And today talk will be about that I'll give is about core collapse and binary mergers in scalar-Gauss-Bonnet gravity. Okay, so yeah, maybe we should too much sharing. Okay, it worked. Okay. The plan of the talk is the following. First, I'll give a very brief overview of black hole scalarization, because I guess you are tired of talks about this in this group. Then I'll follow the discussion of dynamics of such black holes, and more specifically the stellar core collapse. This is the way of forming new scalarized black hole, binary black hole mergers, and descalarization of scalarized black holes. And I will finish with some conclusions. Okay, so let's start with a brief overview of black hole scalarization. As I said, I'll try to keep it very fast in order not to bore you. So what is the whole idea about black hole scalarization? First, black hole scalarization, this is the case when we have theories allowing scalarization. This is the case when we have a theory that has a scalar field as an additional degree of freedom. And we want this theory to be completely in agreement, perturbatively equivalent to general relativity in the weak field regime, but we want the theory to allow for large deviation from general relativity in the regime of strong gravitational fields. And this is exactly the idea behind scalarization. So the theories allowing scalarization practically have this major property. So weak field regime, the same as GR, strong field regime, can differ significantly. And they become so popular because they offer a natural screening mechanism. Because they offer a natural screening mechanism of the weak field gravity and weak fields, which means that all weak field observations are automatically satisfied in these classes. Okay, so so here are summarized the main features of a theory. For a theory to allow scalarization, first, as I said, it should be a theory that has a scalar field, of course. It should be perturbatively equivalent to GR in the weak field regime, allow for scalarization. And I can point out that scalarization is practically a non-linear process, which cannot be modeled with approximate metrics by perturbative techniques and things like, okay, it is not easily modeled. Okay, so what are the conditions for scalarization from a more mathematical point of view? We want this theory to always admit phi equal to 0 to be solution of the field equation. Phi is our scalar field. So practically we want the Kerr and the Schwarzschild black hole to be always solution of the field equation, but we need also a source of the scalar field, and the source of the scalar field starts operating at large space-time curvature and gives rise to a non-trivial scalar field. So the theory that I will mostly interested in the current talk is the Gauss-Bonnet gravity. So this is practically a quadratic theory. It belongs to the so-called quadratic theories of gravity, and terms are the theory is designed in such a way so that the field equation remains of second order, which is not true for all other example of quadratic theories of gravity. And this is how the action looks like. So we have the Ricci scalar, we have a scalar field, we have the Gauss-Bonnet invariant, which is a curvature invariant of second order. And we want this Gauss-Bonnet invariant to be coupled to the scalar field through some coupling expressed here. The field equation that one can obtain after varying this action are the following. So we have an analog of the Einstein equations, where we have the standard term that is the same as in GR plus some contribution of the scalar field, plus this gamma mu, which is actually a complicated function of the metric and its derivatives. And of course, since we have a scalar field, we have a second order field equation for the scalar field. Okay, as I said, so scalarization occurs when we have a GR solution, and at a certain point it becomes unstable and gives rise to a non-trivial scalar field. So this means that intuitively one can imagine that we will have the scalar field becoming unstable, and in order to show this, we take the scalar field equation, we isolate it and consider this equation on a Schwarzschild or curve background, on a GR background, and we perturb it. So after this simple equation is perturbed, we reach the following very obvious equation. The important thing here is that we can define an effective mass. And as you can notice, if this effective mass is less than 0, the perturbation, this would lead to instabilities, and the perturbation would grow exponentially. So this is exactly the condition for a development of scalarization. This is to have a scalar field and with an effective mass, which is a square of the effective mass. Yes.
Sorry, curiosity. What happens instead of squaring Gauss-Bonnet?
It's the Gauss-Bonnet is defined in this way. So it's
okay.
It's not exactly square of something.
Okay, that's right. So why do you have gamma mu? Because this is
gamma
0 in 4 dimensions, right?
No, gamma mu is just I haven't written it here, but it's a very long function depending, as I said, on the curve.
From the Gauss-Bonnet term?
Yes, not directly. I mean, it's not like Gauss-Bonnet term times something, but yes, it comes from the Gauss-Bonnet term.
I thought that the Gauss-Bonnet term gives 0 when you take the variation in relation to the metric. It's not true. No. In 4 dimensions, it's not topological.
It's also if the coupling function is a constant, then this is true.
But one is not
to the field equations. However, when the scalar, the coupling function is non-trivial, the composition is very non-trivial. Also, to integrate by parts.
Okay.
Okay, so we reach here this perturbation equation, and we need a square of the effective mass less than 0. And okay, for Schwarzschild, so let's examine more closely the effective mass. So this, the Gauss-Bonnet invariant, at least for Schwarzschild black hole, is always positive. So let's keep it simple. And then the term, this is always positive, and the term that controls the sign of the whole effective mass is the second derivative of the coupling function f. So this was this coupling function here at phi equal to 0, because we make a perturbation around the background value of the scalar field, and we assume that this is 0. Okay, so when this term is positive, then we have an effective mass larger, effective mass square less than 0, and we have this criteria for the scalarization being satisfied. This means that in order to have scalarization, we don't only have not only need the correct theory of gravity, the correct source for the scalar field, because here the Gauss-Bonnet invariant and the curvature of the spacetime will be the source of the scalar field. We also need a proper coupling between the scalar field and the Gauss-Bonnet invariant. Okay, and how the black hole solutions in this theory look like? So here is a plot of the radius of the horizon as a function of the mass of the black hole. And as you know very well, the Schwarzschild black holes is just a straight line. But if we embed this Schwarzschild black hole in a Gauss-Bonnet gravity at a certain threshold value of the mass, let's say, the Schwarzschild solution will become unstable. So Schwarzschild solution is unstable here and stable here. So this is the point of bifurcation where the Schwarzschild solution becomes unstable, and instead the stable solution becomes this red line here, which corresponds to black holes with non-zero scalar field. So this the red line corresponds to the scalarized solution that are not only stable, but they are energetically favorable. So they will be the ones that would realize in practice, in real astrophysical scenario. And that's why where the excitement in the Gauss-Bonnet theory comes from, because it offers a realistic alternative to the Schwarzschild or the Kerr black hole, which can be actually tested with astrophysical observations. Okay, so this plot here is for one type of coupling function. So here there is a phi squared term in the coupling function, but actually a lot is controlled by this choice. So the first thing that we have satisfied is this condition here about its second derivative, but also the exact form of the coupling function would control how this branch of scalarized solutions look like. And let me just show you one figure about one interesting case that is a little bit more complicated function. So imagine that you have this function here, and you have term with phi square, and we have also a quadratic term in the scalar field. Then the standard picture of scalarization changes a bit. That will be important for the future discussion. So this thing here is now a plot of the scalar charge of the black hole as a function of its mass. So the scalar charge is just the leading order asymptotic of the scalar field at infinity, and this is a measurement, let's say a rough measurement of the strength of the scalar field. So the Schwarzschild black hole is of course the y equal to 0, the x-axis, because it has zero scalar charge, zero scalar field, and the different scalarized solution form these different lines. Okay, so what is the interesting thing here? The standard scalarization that was discovered a few years ago corresponds to this red branch here, which means that this quadratic term is turned off. Okay, but what can happen if we turn on this quadratic term, practically meaning that kappa is different than 0. Okay, so when we increase kappa, you see what happens. So this branch here starts being stretched to the right. And the important thing is that it's not only stretched, but it starts being made out of two parts. So one upper part, this is the stable part of the branch, and one lower part, that is unstable part of the branch. This means that, well, these branches, but this can actually have important astrophysical implications, because you see this branch with the normal scalarization with only quadratic term is smoothly connected to Schwarzschild, because Schwarzschild is the x-axis. But this branch here, the last stable scalarized solution, is not smoothly connected to Schwarzschild. And for example, just imagine that we had a black hole that was somewhere here. This black hole was secreting more and more matter. Eventually, it would not smoothly go to a Schwarzschild black hole as it will be here. Like here, the scalar field will decrease and the black hole will just turn into Schwarzschild or Kerr. Here, the scalar charge will decrease, and then there will be a jump to a completely different state. So this jump will be something interesting that we'll be discussing at the end of the talk as an astrophysical implication. Okay, but then the question you should ask is, what are the constraints of this theory? Because we already have some weak field regime of gravity is constrained perfectly well, but also already there are some observations that more or less can constrain with a good accuracy some features of modified theories of gravity. And here is one such example of the constraints coming on this theory from binary pulsars, because it's not only black holes that you can scalarize in this theory. Actually, it's even simpler to scalarize a neutron star because they have matter. Matter can also act as an additional source of the scalar field. So scalarization is in principle easier. And why binary pulsars? Because there are a lot of binary pulsars observed. So these are pulsars in closed binary system. So people are practically observing the shrinking of the orbit of this binary pulsar due to emission of gravitational waves. So the problem, at least the problem for alternative theories of gravity, is that what people observe as gravitational wave emission, so practically shrinking of the orbit of these closed binary pulsars, is that it matches perfectly well to general relativity, and there is no really room for deviation. Okay, so how this translates to modified theories of gravity? In modified theories of gravity, normally we have an additional degree of freedom. An additional degree of freedom means that we will, in most cases, have an additional channel of energy loss. This means that such an additional channel can be the scalar dipole radiation, and this means that if the two pulsars were orbiting, so if this theory was correct, and if the two pulsars were scalarized, then during their while they're orbiting around each other, apart from the tensorial gravitational waves, they will also emit scalar dipole radiation. That will be an additional channel of energy emission, and the two pulsars will be spiraling faster than in general relativity. So practically, by observing the dynamics of such pulsars, we can say whether there is an additional channel of energy loss or not. And for now, at least the astronomers claim that there is no such a channel. This means that at least the pulsars that we are observing out there in the universe should not carry scalar charge or should have, let's say, zero scalar field. More or less, let's talk about this later. Okay, so then what we can do? So one can design a general coupling function between the scalar field and the Gauss-Bonnet invariant, and one can plug in parameter here in this coupling function. That is practically the parameter instead of the pi square term, and we also have one lambda term here. So practically the full coupling between the scalar field and the Gauss-Bonnet invariant is this one. So this carries the functional dependence on the pi, on the square, on the scalar field, and this carries lambda square, practically the dimension of the coupling function. So only the combination of these two can give you the full coupling. And then for binary pulsars, and from the lack of observation of any additional channel gravitational wave observation, we could put an upper, eventually an upper limit on the maximum mass of scalarized black holes. So the constraints from the binary pulsar practically could translate to what is the maximum mass of a black hole that can scalarize, which is extremely important because, well, from neutron stars, we can translate directly the constraints to black holes. And what we observe, so this is a plot of lambda as a function of beta, and this is a contour plot of the mass of the black holes. And these two lines here corresponds to the constraints coming from different equation of state. Let's say that all the modernist equation of state will give you lines between these two. And as you can see, only black hole masses located in this region here are allowed by binary pulsar observations. Okay, and if you can read from the graph, this means that we can have black hole scalarization only for black holes with masses between 15 and 10 solar, between 10 and 20 solar masses, which is not that much. Sorry? No, no, but it's so it has some there. So practically it has a slope like this, but you cannot observe it on this scale because for this coupling, it turned out that the binary pulsars constrain so well the theory that the slope here is so negligible that even we could hardly see it for most of the cases. And yeah, okay. So why this is in a case problematic for further testing the theory with black holes is because one of the major goals of the major hopes in the gravitational wave observations is that we'll manage to know more about the strong field regime of gravity from binary black hole mergers. But we already know that from binary pulsars, we already know that neutrons, black holes more than, I think that it will be again 10, 15 solar masses if we take really new data and so on, cannot scalarize. This means that most of the gravitational wave events eventually, for sure, won't have a scalarized black hole inside the binary, which means that in order to constrain further the theories with black holes, we should always, with black hole mergers, we should always search for a not very massive merger of black holes, at least in one of the companions. Okay, and now let's proceed to the dynamics, and let's start with something simple. So once the solutions were constructed, of course, the most standard thing is to study the dynamics, but of course, this is much more difficult than constructing the solutions themselves. Why? Because, well, this is doing the evolution is in many cases is complicated, and also the Gauss-Bonnet, the inclusion in the theory of the Gauss-Bonnet invariant makes the picture and the analytical and numerical calculations much more involved compared to pure general relativity. So let's start with the most simplest case of this is what historically started, of a scalar field around a black hole, and see the evolution of this scalar field. Okay, so this is how the profile, how the evolution of the scalar field as a function of time looks like. So practically any initial perturbation of the scalar field would grow exponentially. So this is a straight line because this is a logarithmic scale. So there is an exponential growth, which comes exactly from the fact that we have an effective mass less than 0. But at a certain point, a nonlinear effects would kick in, which means that we will have this the nonlinear effect will practically stop this exponential growth and allow for the system to settle down to an equilibrium solution. Why I'm showing this is because it turns out that we can simplify the study of the dynamics a lot and still get a lot of information about what's actually happening. So imagine the following case. So imagine that you freeze completely the metric and you consider only the evolution of the scalar field. This means practically the generalization of the Einstein equations remain the same. And we have only one equation for the scalar field, where in this equation, we only allow the terms in red to evolve. This simplifies, of course, the system a lot. And you might think that this is a very crude approximation, but the truth is our tests show that it's actually very accurate, both qualitatively and quantitatively, if we consider scalar field that is not strong enough. So for weak scalar field, such an approximation is quite good, and it helps us much faster and much easier to study the dynamics. Why this is important? Because while doing dynamical evolution of scalar field around the non-rotating black hole, that's the case here, it's not that interesting. This problem can be not easily, but is quite manageable, both in GR and in Gauss-Bonnet gravity. But if we go to 2 dimensions, if you go to axially symmetric space-time, then the situation is much more complicated. And for now, yes?
Sorry, in the previous slide, both galaxies side at the horizon?
Yes.
And in the other places also.
Sorry?
In the other places, what happens to the field?
Is the same. So it's so practically this figure wants to show that any small perturbation grows exponentially and settles down to a constant value. And this constant value will be different at different points in the space-time, but the general trend is the same. Okay, so what about rotating space-time? Because there, as I said, at least until now, I'm not aware of anyone that has managed to do the evolution of scalar field around an isolated black hole if the black hole is rotating. But I mean, in the full theory, but if we consider this decoupling limit approximation, things become manageable, of course, because the equations are much simpler. Okay, so what one observes, so these are the full profiles of the scalar field. This is the radial coordinate, the turquoise coordinate, but just some function of the radial coordinate as a function of theta. And the different surfaces here correspond to the profile of the scalar field in different time frames. So practically, again, here, we start from a negligibly small scalar field, and as the scalar field evolves, it rises quite quickly and then eventually settles to an equilibrium configuration that is the blue surface here. So practically in this way, we can study not only the evolution, but also the final state and how the final scatter field around the black hole looks like. And why this is important, because this can be applied also for other theories of gravity, like the dynamical Chern-Simons gravity, where at least for now, finding even the stationary axisymmetric solution seems to be a bit hopeless task. Not that it's not impossible, not that it's impossible, but let's say it's extremely difficult and people haven't managed it that far. So what is Chern-Simons gravity? Let's go a little bit back. So this is again a quadratic theory of gravity. So we have the Ricci scalar, we have a kinetic term of the scalar field, but instead of the Gauss-Bonnet invariant, we have the Pontryagin invariant, which is actually another complicated function of the metric and its derivatives. And the important thing about this theory is that it differs from GR only in the presence of pod parity sources such as rotation. And as I said, for now, there's only one paper that finds stationary and axisymmetric black hole solutions in this theory, rotating ones, but they're not scalarized, they are a bit different. So for scalarization, there is nothing. But through this decoupling limit approximation, we can study how the final profile of the scalar field would look like. And here are two figures only of the final scalar field profile that is obtained through the evolution of the scalar field equation. Sorry? So to be honest, we haven't thought about spin-induced scalarization in this theory. So for the spin-induced scalarization, it's important that the Gauss-Bonnet invariant at certain point changes sign for rapid rotation, and we haven't studied what happens with the contrary. So in that case, there are studies only of the normal scalarization. I don't recall anyone studying whether, so this is for one sign of the coupling function. I don't remember, so there's no paper about the opposite sign of the coupling function, which would be similar to the spin-induced scalarization. Maybe social agreement, can the contracting density change sign for, so it's possible, okay. We haven't studied this, and no one else has studied this. So, but it's quite easy to do it. But yeah, this is a very interesting project that you're proposing, that you're saying. So the interesting thing about this stationary solution is that here the scalar field has quite distinct profile compared to most of the other cases. So this here is again only the final profile of the scalar field. This is the radial coordinate, this is the angular coordinate. And notice that here, okay, so this here, the angular coordinate goes from 0 to pi, which means that this corresponds to one of the poles, and this corresponds to another pole of the black hole. So here, around one of the poles, we have a maximum of the scalar field, and around the other pole, we have a minimum, which means that there is like a scalar field cap around one of the poles of the black hole, while there's almost no scalar field from the other, which means that this can have interesting implications on the astrophysics of this object. Okay, and let's now finally go to realistic cases, realistic dynamics, because until now we spoke only about the evolution of scalar field in the near vicinity of a black hole, but this was really a model case. So what would happen if we put this black hole and we put this perturbation, what would happen? So this is not really a realistic astrophysical scenario. This is a model case that we want to study and to demonstrate how the scalar field evolves. So the real astrophysical scenarios where new black holes form is stellar core collapse and black hole mergers, and I will discuss them one after the other. Okay, so let's start with the stellar core collapse. So this is practically the collapse of the core of a normal star that remains after a supernova explosion. So due to the gravitational force, it collapses to either a neutron star or a black hole. Well, we forget about the white dwarf case here. Okay, so the normal GR picture is we have this core collapse and either a neutron star or a black hole forming. But if we allow for this scalarization, we can have many other interesting scenarios. And here is a summary of the possible outcomes of a core collapse in Gauss-Bonnet gravity. Okay, so first we discussed that for certain sign of the coupling function of its second derivative, it's possible to have black hole scalarization. That is this case here. For another sign, it's not possible to have black hole scalarization, but it's actually possible to have scalar care around the neutron stars. And let's see what are the outcomes. So once the star collapses, it can have a proton, it can form a proton-neutron star with a scalar field. It can form a proton-neutron star with scalar field, and then this scalar field survives and is amplified when the black hole forms. The scalar field can form also only after the proton-neutron star collapses to a black hole. And another interesting case in this here is when the core collapses, it forms a scalarized neutron star, but then because in this case we don't have black hole scalarization, all the scalar field is emitted and we are left with a bulk black hole. Okay, and we have actually performed this simulation by considering in this time the full coupled nonlinear evolution of the system. So when taking into account of the back reaction of the scalar field on the matrix, so we use some modification of the GR1 T-code.
So that in this case, you don't have black hole scalarization. Why does that not happen in this case and it does happen in other cases?
The sign of this coupling here.
Or why is it different in this case versus in the other cases? Is it just you chose F differently now?
These are different theories. So this is theory with this sign, and this is another theory with another sign.
Okay.
So whether you fall here or here, in which case, you fall depends on two things: on the parameters in the theory, like on the choice of the coupling function and the parameters inside of the coupling function, and also on the properties of the progenitor. So the progenitor more or less tells you whether you form a neutron star or the black hole, and then the parameters of the theory more or less control these different cases, like whether it's this one or this one depends mainly on the theory parameters, or like this one or this one. Okay, so for the actual simulations, we have chosen the collapse of a 12 and 40 mass stellar core, which in one case led to the formation, in the first case led to the formation of a neutron star, in the second case led to the formation of a short-lived proton-neutron star that quickly collapsed to a black hole after subsequent accretion. And here are some graphs for the time evolution of different quantities for two of the, I think, most interesting cases when we have the core collapse into a scalarized proton-neutron star, a scalarized black hole, and for the case when only in the intermediate phase we have a neutron star scalarization. Okay, so these are a little bit overcrowded graphs. So, but now let's concentrate on only one thing. Let's concentrate only on the blue line here and here. Why? Because the blue line is exactly the dileton charge, which was the measurement of the scalar field that is the lead decoder asymptotic of the scalar field at infinity. Okay, so how does scalar charge behave? So here, the scalar charge is first 0 as the star collapses. It raises once as the star forms, and it raises a second time as the black hole forms, and then it remains constant, which means the settling of the final equilibrium solution. In this case here, the scalar charge is 0, then it starts increasing, which is the formation of this proton-neutron star, but as the black hole forms, it sharply drops to 0, because in these cases we have the no-theory theorems which forbid the existence of scalar here. Well, here this code is spherically symmetric, and we could not see how this would affect the gravitational wave emission. So this will be a next step to go away from spherical symmetry and to see how all these cases would actually affect observables of the core collapse. Okay.
Where is the scalar going in our space? Is it being absorbed by black hole?
So both. So the scalar. So part of the as this neutron star collapses to a black hole, whatever is left inside the horizon stays inside, and the small amount of the scalar here that is left outside the black hole, a big portion of it is radiated away. So that's why this case is interesting, because we have a relatively large portion of scalar radiation to infinity and loss of energy. Okay, so, but there is another problem that exists in this type of dynamical simulation, and this is the loss of hyperbolicity. Because the moment when you consider the coupled evolution of the scalar field and the metric and Gauss-Bonnet theory and in many other quadratic theories of gravity, then the equations might lose their hyperbolic character that is happening for large space-time curvatures. So what's happening? So the discriminant of the characteristic equation, this is just some mathematical defined quantity dependent on the coefficient in your evolution equation. And when this quantity, when the discriminant becomes less than 0, the hyperbolicity of your system is lost, and we have a system of equation of mixed character, something that we had a talk about yesterday. Okay, and indeed, this is one of the cases. Not really. So every person, if you talk to different persons in the field, you get different opinions. So some of the people can tell you that this completely kills the theory. So if there is loss of hyperbolicity, then the theory is killed. Then there are people who would say that this loss of hyperbolicity, because it happens only for small black holes, that this loss of hyperbolicity is due to the fact that for small black holes, which means very large space-time curvature, we should cure the Gauss-Bonnet theory with additional term, because the excuse for Gauss-Bonnet theory is quantum gravity, and let's say that there should be more curvature invariants of any order appearing and being active. And there are people claiming that this is a gauge choice. So by choosing a different gauge, this can be changed. I'm not so confident about this last statement, but like you can get all types of answers depending on the person you talk to. But this is a problematic sector of the theory, and this is not a specific thing for Gauss-Bonnet gravity. This is in Gauss-Bonnet gravity. This is in Chern-Simons gravity, no quadratic theories of gravity. This happens in many places. So once we go away from pure scalar tensor theories, we normally run into problems and have some problematic sectors of the theory. So this is the truth. We still don't know how to generalize Einstein gravity well. Okay, so this is how the discriminant evolves. So this is the radial profile of the discriminant at different time slices. And this is the case when we lost hyperbolicity. And as you can see, the discriminant at some point starts becoming negative, which means that the simulation crash and they cannot evolve further. The problem is that this happens for relatively strong. This happens for relatively weak scalar fields, which means that due to this loss of hyperbolicity, we could not dynamically construct neither a neutron star nor a black hole with a strong scalar field. So one should find a way to go away from this, or admit that this is a problematic sector of the theory. No, so this theory about the gauge choice, to be honest, so I've started hearing this only recently. So this is one of the things that I'll be interested in some people experimenting. So practically there are not that many, but still enough simulations in Gauss-Bonnet gravity, and all of them use different type of gauges, and for now, all of them crash. So there is no way to, I haven't seen a serious study on this that really sees that if we change the gauge from this to that, we cure the loss of hyperbolicity. This is more like a statement for theorists, not the numerical people do not agree too much with that. For now, at least this is my feeling.
then change the condition. Not so. So I wouldn't be 100% pessimistic about it. They did. At least that's a question that should be looked at.
Yes, and I'm sure that while we are speaking, there are people not looking for this apart. So we are not looking at this, but I guess that there are people who look at this at the moment. So I'll be very interested about the paper appearing on this. Okay, and the last thing I'm going to talk about is the black hole merger. And in the previous slides, we 10 minutes? Yeah, it's perfect. In the last slide, we discussed the formation of new scalarized black holes. But what if we have a merger of two black holes? Then something, the opposite effect happens. Why? So let's remember this graph, which was the radius of the horizon of the black hole as a function of its mass. Here, the black line of the charged black hole, and the scalarized solution were the red line. So existing only in this region here, which means what? That only small mass black holes can scalarize. So obviously, when two black holes merge somewhere here, they'll end up either gaining the scalarized window or outside of the scalarized window, which means that after the merger of two black holes, of two scalarized black holes, you can either create a new scalarized black hole, or you can create a bulk black hole, a black hole that loses its scalar here. So practically the merger doesn't lead to black hole scalarization, it looks to black hole descalarization. And this was shown for the first time by Silva and collaborators a year ago. So they considered the merger of two black holes. This is head-on collision, and the black hole had initially scalar here, and as they approach each other and as they merge, a new descalarized black hole, practically a third black hole, was reached at the end of the simulations. Okay, so this is, I won't go into too many details about the standard scalarization. I'll just, instead, I'll try to advertise another effect that is happening, that is again dynamical descalarization, loss of scalar here, but for another type of coupling function, because all the studies here are for the standard cases when we have a coupling function depending on the having a term proportional to the square of the scalar field. But if you remember, if you make the function a bit more complicated, if you allow both quadratic and quartic terms in the scalar field, we could have this jump between scalarized and non-scalarized solutions. Okay, so in this figure here, this is a plot of the scalar charge of the black holes as a function of mass of lambda, and lambda was a coupling function. So this is related to this is the dimensional part of the coupling function, and everything here is normalized to the mass. Well, now everything is a little bit turned around compared to the previous graph, but just because it's easier represented for the mergers. And the charge of solution is again the x-axis because it has a zero scalar charge, and the standard scalarized black holes are the blue line, which means this term turned off, k equal to 0, and black hole solution going smoothly from high scalar charge to zero scalar charge, that is Schwarzschild. But the red line, if you remember, this was the case with quartic coupling, where it was possible to have this part of the branch stable, this unstable. So practically one can observe a jump in the scalar charge of the black holes once we reach this point from here to here. And this is something that hopefully can be observed by the binary merger observation. So what is a toy problem as a initial step? We did the following. We consider binary black hole merger for this coupling function that I showed you before in the decoupling limit approximation. So when the back reaction of the scalar field is neglected. For the numerical simulation, we used a modification of the NURBI code, which uses a BSSN formulation of the equation in spherical coordinates, and we performed head-on collision of two equal mass black holes. Even though all this is, of course, quite an approximation, quite a strong approximation, this is still sufficient to study qualitatively the effects from jump from one scalarized solution to a non-scalarized one. Okay, and let's start with the case of standard scalarization with k equal to 0, so practically only this term active. And this is the blue line when we had a smooth transition between scalarized solution and Schwarzschild, which is this one. Okay, and this is how the profile of the scalar charge of the scalar field at infinity multiplied times r would look like as a function of time as the merger proceeds. So here is the waveform of the merger. So, and this more or less is the moment when the two black holes actually merge. And this waveform is not, this is the tensorial waveform. This is not modified because we are considered the coupling limit approximation, no back reaction on the method, but we have shown it just in order to see where exactly the merger happens. And this here is the profile of the scalar field at infinity, the scalar charge. We start from a very small perturbation of the scalar field. The scalar field rises because we have chosen parameters where the individual black holes can scalarize. And eventually, as the merger happens, that is around here, the black hole, the scalar field decreases and it either settles to a equilibrium, constant value, or it decreases slowly with time. So which cases of this here will happen will depend on the parameter lambda, which is connected with the coupling. So the full coupling is lambda times f. So the stronger coupling between the scalar field and the Gauss-Bonnet invariant, the higher we get from here to here. Okay, so what is important here, the message from this figure is that as we vary lambda, practically the coupling strength, we reach from the red to the green part of the figure smoothly. So there is no any significant change happening here, which means that if we observe many black hole mergers, we will have a smooth transition between a scalarized black hole and a black hole which has nearly zero scalar field to a completely descalarized black hole. But what if we allow for this Quadratic term? So this case is beta equal to 6, k equal to 16. So practically some parameters here that allow for this red line to exist and for this jump here to be present. Okay, so here is again the evolution of the scalar field during the black hole merger. And it's again for different choices of lambda. As you can see here, this distinct feature of a jump between scalarized and non-scalarized solution is observed here. So in the beginning, as lambda is varied, we reach constant values of we reach constant values of the scalar charge, which cluster practically to some value here. And if we slightly decrease lambda a little bit more, we jump from this regime to this regime, which means that we don't have a smooth transition between the scalarized and non-scalarized case. And this is something that can clearly observed also in the gravitational wave signal. Well, in order to observe it, we should consider the back reaction on the tensorial waveform and how the actual gravitational wave signal would change. But already these simulations here bring us the message that this coupling with Quadratic term being active can lead to some interesting consequences. And for example, one can search for analogy with the binary mergers of neutron star, allowing for first order phase transition from confined nuclear matter to deconfined quark matter. This is practically when the two black holes merge. During the merger, we observe the formation of deconfined quark matter core of the new neutron star. So such jumps are also observed for. Sorry. Sorry? So if you turn on the yes, so things like this would be possible, yes. So there will be again a jump, but then the solution, the spectrum of solution is quite different from GR, not from GR, from the standard scalarization. So this is what we call nonlinear scalarization, and this is if only this term is active here, then Schwarzschild will be always stable. There won't be unstable part of Schwarzschild. But we will have also the scalarized black hole existing. Well, in a different, this will be a completely different picture. I don't have it here. And yeah, a jump between the last stable scalarized solution and Schwarzschild could be also possible, but there are some more subtle problems. There is how these black holes have formed, how to excite the scalar field, and so on. So this, since this is more standard, we have started with this. Okay, yeah, so this is just a remark that such jumps between solutions is actually already observed also, this model also for neutron stars, and hopefully one can use the methodology developed for neutron stars, at least some aspects of this methodology, also for searching for such phase transition for black holes, and eventually the lack of the observation of such phase transition or the probable observation can really put very strong constraints, not only on the theory of gravity, but also on the type of coupling that is possible, because we know nothing about what is the true coupling in the theory, right? And let me finish with some conclusions. And let me just say that scalarization is a very interesting phenomena. I hope I have convinced you with this, and it helps endow a black hole with scalar here while leaving the weak field regime of the theory unaltered. Scalarized black holes can form in realistic astrophysical scenarios like the core collapse, while the merger would lead to might lead to a complete loss of the black hole scalar here. And depending on the parameters of the theory and the coupling, the dynamics of this system can eventually lead to both qualitative and quantitative different picture from GR that can hopefully be eventually tested. So thank you very much.
Thank you very much. Do we have questions now for the speaker? I think Giorgio was first.
Why did you choose the function for the coupling? There are people who choose that specific.
So, right on the blackboard. Oh,
Sure, yeah,
no, I mean, so I think it's. Yeah, it's completely. Okay. So practically, what you need, this looks quite complicated, right? Because it's a summation of two terms, one plus exponent. We also have an exponent. You might ask why this is. So first, these coefficients here are just made for normalizations. We want the first we want some derivatives to be of the coupling function to be 1 at 0 scalar. So some of the coefficients are just for easy thing, for having a better normalization. Then at the end, what you need in order to get something similar is like something like this. And so the leading order term here would practically would depend on pi squared here and pi to the power of 4 with different coefficients. And also in a theory like this, we can also have similar examples and similar cases happening. So this particular choice with the exponent instead of a linear function here is just chosen for numerical convenience. Because why? Because if you choose just f of pi proportional to pi square, then actually all the scalarized solutions are unstable. So this is a problematic. One should add higher order terms, one should put exponent here or something like this. Then just this is a general observation for the numerics that it's better instead of doing something like this, putting an exponent, which doesn't seem very good physically motivated, but you can always think that we don't care so much about the exponential behavior, we just consider the leading order terms here. So this is just for convenience, not so that we don't have to explore that much of the parameter space to find stable where we have solutions.
Maybe we can follow up to that. Why not keywords?
It's possible as well, but so we have problems finding a nice solution with cubic behavior and nice stable solution. So we always started actually a little bit the other way around, not because the dynamics you can always perform with any coupling function, but we wanted at the end not only to have dynamics here, but we actually always wanted to start from the existence of a stable, well-behaved black hole solutions, and then translate to the dynamics here. So for the cubics, we had problems. One colleague actually found some solutions that we are still studying, but this was the quartic term, the addition of the quartic term somehow led to much better behaved solutions.
When you say found some solutions, you mean like impose the statement is static and then solve the
Yes, found solutions like this, static and spherical symmetric. Yes. So because as I said, we always try to search for this. Are these solutions exist and are they well behaving, and then go back.
Is there any physical thing happening when the spherical changes sign for the small number?
So here the equations are invariant under change of sign. So so this practically depends on the modulus of. So you can everywhere you can assume like a modulus of the scalar field. So the same solution. So actually this graph here exists. The same graph exists for the negative. For negative scalar charges, we never this is a change of Sakar of the sign of the scalar field, but the field equations are invariant under this change of sign, and the metric remains the same. So it's not a new solution. So we care only for one of the signs.
I think Antoine was first, and okay.
And so what about the cosmological solutions and theories? Because for the original scalarization, they were abandoned because there was a problem of like it was working for local solution, then it was some instability.
What do you mean original? The more specific Resi model? Or the
storage scalar.
Sorry?
It covers to reach scalar instead of covering Gauss-Bonnet and
So scalarization in general has problem with cosmology. Yes, you're correct. So,
but like if you put the scales that are interesting for black hole scalarization,
it has
problem.
So it has a problem, but the late time evolution of the universe can be cured. The problematic is the early time evolution of the universe. So there are strong claims that there are problems with the inflation. But still, inflation is not like this strict theory that you put and you discard every theory afterwards. So I believe that with the proper choice of this theory and with inflation, maybe this can be cured. But yes, with the standard and with the original Gauss-Bonnet gravity and some of the standard understanding of inflations, yes, there are problems that still cannot be well overcome. Sorry? Yes.
Yeah, they're come down, so that contains first derivatives of the square or
Second derivatives as well. Or not only first. What do you mean nothing else?
So I mean, the heuristic, I mean, the different breaks and sides a good or bad, so is the gamma.
Yeah, mostly yes.
It's not mainly second derivatives in the RGB.
No, but this equation alone cannot lose hyperbolicity. Only the system can lose hyperbolicity, and he's right. Yeah, maybe I couldn't.
You do need so there are second derivatives buried inside the RGB. If you consider the coupled system, then they're also principal in the RGB square.
Yeah. Yes.
So if it's in a fixed background, I'm not arguing with you, right? A fixed background of this.
Okay, yeah, Diogo.
This one?
Yeah, you mentioned that it's not so what we want to
Yes. Because of the property of the theory and the way the Pontryagin invariant is constructed, it just it has axial symmetry, this solution, but it doesn't have a symmetry with respect to the equator. While this, I mean, I haven't showed it that much. So here, the angle for this is for Gauss-Bonnet gravity goes from 0 to pi over 2, and then everything repeats. So what is here, then we have a symmetric part after pi over 2. Here, because of the nature of the theory, we don't have symmetry with respect to the equator. So we can either have one maximum here, minimum here, maxima with different intensity, and this doesn't normally happen in modified theories of gravity. So this, no, there is a physical. It comes from this term. So this term is bringing the violation of the parity invariant. So this is already in the theory from the inclusion.
I was just thinking there's any classical system.
There are a few more papers. So for Chern-Simons gravity, because of this term here, this always can happen. No, it doesn't happen always. It happens in some cases. It's not a general feature, but it happens in some cases. As far as I remember, there were also some other exotic black hole solutions where this was also happening, but I cannot, I mean, if you want, I can send you the papers. There are a few known solutions like this black hole. It's not like 20, it's like a handful of solutions.
Okay, we are running out of time, so unless there's somebody really needs to ask a question. So to be the case, I suggest we can speak again.
If you enjoyed the video, like and subscribe.